Good morning. This lesson is from our Trig-Precalc class, but before I get started, I want to say I hope everyone is doing all right out there. I don't remember what lesson this is. This might be Unit 5 or Chapter 5, Lessons 5 or 6. That doesn't matter. I'll title it correctly in the video. But what does matter are our goals for the day. We have 4. Our first goal is going to be to review the Pythagorean Theorem. Our second goal is going to be to relate the Pythagorean Theorem to trig ratios. Our third goal is going to be to create Pythagorean identities. And our fourth goal is going to be to define secant of theta. I'll explain what that means later. Cosecant of theta and cotangent of theta. And we're going to insert these into the Pythagorean identities, PI, Pythagorean Identities. So let's just go ahead and jump into our first goal here. And it's just a review of the Pythagorean Theorem. I want to give you a little bit of a lesson about it. It's a little bit more than the equation a squared plus b squared equals c squared. So we'll just spend a little time with that with this review. So Pythagorean Theorem is an equation for right triangles. And so my right triangle has side lengths a, b, and hypotenuse length c. I get the equation a squared plus b squared equals c squared. Now, the equation is really about squares that can be made off the sides of a right triangle. The simplest right triangle has side lengths 3, 4, and a hypotenuse length of 5. If I plug it into the Pythagorean Theorem, I get 3 squared plus 4 squared, and that's going to equal 5 squared. 3 squared is 9, 4 squared is 16, and 5 squared is 25. 9 and 16 gives me 25, and that's equal to 25. So this is what you're most likely familiar with as a right triangle. Just the equation, but you rarely see the picture that represents this equation, and I'd like to just draw that for you here. So what I'm going to do is draw my right triangle. I'm going to try not to make it too big so that I can draw it properly, and if I can draw a straight line, that would be awesome. Okay, let me make that a little bit longer. I'll make that work. That's okay. There's a reason why I'm not an art teacher. Okay, so this would be my side length of 4, this would be my side length of 3, and this would be my side length of 5. And again, the equation actually is about the squares that come off the side lengths. So if I made a square off of this that had length 4, you know, I come down like this, and then I come over like this, and I come down like that. And since it's a length of 4 by 4, what I'm going to actually get here is I'm going to get, let's see here. So this would represent a square with side lengths of 4 by 4. And then see in here I have 16 little squares. That's this. Off the side length of 3, I'll make a 3 by 3 square. Let's see, how do I do that? Oh, it's like this, okay. So, off the side length of 3, I get a 3 by 3 square that has 9 little squares in it. And then off the side length that's 5, I'm going to probably have to draw into this. Oh, it's close. I'm going to get a square that has side lengths 5 by 5. So let me go ahead and draw that in here. Let's see if I can do this. I wish I could add some sound effects. I'd put a drum roll right now. This is 1, 2, 3, 4, 5. Okay, it's a little off. It's a little off. But in this square of 5 by 5, I'm going to have 25 little squares. So the amount of little squares that I can make off one leg and the amount of little squares that I can make off the second leg are going to add up to be the amount of little squares that I can make off the hypotenuse. So again, the Pythagorean theorem is really about the squares that you can make off of the side lengths. I'm going to go ahead and pause this here. I'm going to erase this. I want to discuss a way that people argue that the Pythagorean theorem is true, and it has to deal with the squares, right? So let me erase this, and I'll be back. I'm back. So we're continuing our first goal, and I want to tell you a story. I'll try and make it short, and hopefully I can articulate it well enough. But let's pretend that this is a room. Okay, this is a room, and in this room, I'm going to put 3 area rugs. I'll put a rug right here. I'll put a rug right here. And I'll put a final rug right there. Okay. So the rugs are covering a certain amount of the floor, which means that there's a certain amount of the floor not covered, right? So there's a certain amount of floor not covered. So if you understand what I'm going to say next, you understand how the proof that I'm going to show you actually works. So there's a certain amount, I don't think I spelled that right. Certain, oh gosh. Certain, oh, how do I spell certain? Certain, I'm going to leave it like that, and it will make my board be a smart board. Certain. There's a certain amount of floor not covered. Where was I? Yes. So what I'm going to do is I'm going to just assume that this room, the feng shui is off. And so it doesn't have a positive energy flowing through it because the rugs are in the wrong spot. Now, if I move the rugs around and they're not overlapping, there's still the same amount of floor not covered. So moving the rugs around, I still have the same amount of floor not covered, right? No overlapping. That's very important. No overlapping. Moving the rugs still leaves same amount of floor uncovered. Okay, so that is the background knowledge we need to have in order to hopefully understand this argument I'm going to make. And this argument I'm going to make is thousands of years old. I mean, it's not a new argument. It's thousands of years old. So what I'm going to do is I have a square, and I'm going to draw 4 identical right triangles in it. I already marked it off so it will be perfect. So here's one right triangle, and here's another right triangle. Let me connect that correctly here. There we go. All right, there we go. And here's another right triangle. And here's my last right triangle. Okay, so what we have to do in this situation is we have to imagine that the triangles are the rugs. Rug, oh, I don't know if I can write it this way. Rug, rug, and rug. Okay, so these rugs are leaving this amount of floor uncovered. So this is uncovered. I cannot spell. That's why I'm not an English teacher. There's more English than spelling. This is uncovered. And this square is the square off of the hypotenuse. Okay. Alright. I just realized I didn't draw this next one right. I didn't mark it off right, but that's okay. I'll make it work. Alright. So, with this previous example, hopefully you understand that if I move the rugs around and they don't overlap, the same amount of floor is still uncovered. Here I have 4 triangular rugs, and the uncovered part of the floor is the square that's made off the hypotenuse. Remember, the square that's made off the hypotenuse will be as large as the squares made off the 2 remaining legs. So if I move the rugs in such a way, I guarantee that I can have the 2 squares off the hypotenuse being the remaining uncovered part of the floor. And let me just do this real quick so I do make it right. Okay, so I apologize real quick. This is going to take a second. I need to do this so I can do it correctly here. You know, there we go. All right, I think I fixed it. Okay, so what we're going to do is we're going to move this rug across in this direction, and it's going to make a rectangle with this rug. So I'm going to get something that looks like this when I move it across. So my 2 rugs combined together and they made a rectangle, right? This rug slid up to that rug. Okay. Now, what I'm going to do with this rug and this rug is I'm going to slide this rug over in this direction, and I'm going to come straight up with this rug. It's a little hard to follow along, I apologize, but here's what we're going to get. So I get that. That rug comes up like this. And then here's my final rug. Okay, so here's a rug. Here's a rug. Here's a rug. And here's a rug. Remember, if I move my rugs around and they're not overlapping, the same amount of floor is still uncovered. And in the original picture, the amount of floor uncovered was a square off the hypotenuse. In this new picture, the floor that's uncovered is a little square off one of the legs, so this is uncovered. This is an uncovered square. And it's off one of the legs. And this is an uncovered square. And this is off of the other leg. So this shows us that the square that comes off the hypotenuse must be as large as the squares that come off the legs, because again, the rugs aren't overlapping. They just got moved around, and what's not covered must be the same size. So I'm going to go ahead and end this here. Hopefully that made sense. And I'm going to go ahead and start talking about our second, third, and fourth goal. So I'll be back. I'm back for the 3rd time, I think. Oh, well. We're on to our second goal, and it's going to be to relate the Pythagorean Theorem, which is about the squares that could be made off the side lengths, to the trig ratios. So let's just review the right triangles we've been working with. The right triangles we've been working with are in the unit circle, so the hypotenuse length is 1, the horizontal length has been x, and the vertical length has been y. So here's an example of a right triangle that we've been working with in the unit circle. My hypotenuse length is 1, my horizontal length is x, and my vertical length is y. Now this symbol right here, we're going to introduce it to represent unknown angles. So we do this to students in math, right? Remember, multiplication symbol used to be an x, and then we took that away and it became a dot, and then the x represented the unknown. Well, if I use this as an x, I already have an x for a horizontal length, so we use this symbol, which is called theta, and we are going to use theta to represent angles. So that way I'm not using x twice in the example here. So let's go ahead and I'm going to write the Pythagorean theorem for this. So first I'm going to write the Pythagorean theorem. There's a marker I would like to use. First, the Pythagorean theorem. And it's going to be x squared plus y squared equals 1 squared. All right. Second, I'm going to write the trig ratios. So cosine of x is the adjacent or the hypotenuse. I'm not cosine x, cosine of theta. I just told you guys it was going to be theta. Cosine of theta is equal to the adjacent, which is x over 1. So cosine of theta becomes, or is equal to x. So cosine of theta is equal to x. Sine of theta is equal to the opposite length over the hypotenuse. So that's y over 1. But y over 1 is just y, so sine of theta is equal to y. I'm leaving out tangent for now. We don't need that quite yet. But notice that x is equal to cosine of theta. So what I'm going to do is I'm going to plug cosine of theta into the Pythagorean theorem, and I'm going to plug sine of theta for y into the Pythagorean theorem. So I'm going to plug cosine of theta in for x and sine of theta in for y, and rewrite the Pythagorean theorem. THM is good enough for theorem. Let me make sure I'm in the viewfinder here. Oh, I'm gold. All right, so x now becomes cosine of theta. So I get cosine of theta, and that's being squared, plus, instead of y squared, I'm going to say sine of theta. So it's sine of theta being squared, and that's equal to 1 squared, which I can just call 1, right? Now, when I square a cosine, I go cosine squared of theta. I don't square the angle, I square the cosine, plus sine squared of theta is equal to 1. So remember, I wanted to relate the Pythagorean theorem to trig ratios. I got 2 trig ratios inside the Pythagorean theorem, so I think I actually really did accomplish the second goal really well, and I think I did do the first goal. Okay, so I'm going to go ahead and end this, or stop here, erase everything, come back and talk about the third goal. By the way, we did create one of them already, and then from there we'll jump into the fourth goal. So let me erase everything and I'll be back. I'm back again. It's like the third or fourth time I've been back. But let's go ahead and jump into our third goal. And our third goal is to create Pythagorean identities. Now we already created one Pythagorean identity. Cosine squared plus sine squared, cosine squared of theta plus sine squared of theta equals 1. To find the second Pythagorean identity, we're going to divide the above equation by cosine squared of theta. So I have the above equation. I'm going to divide everybody by cosine squared theta. So let's see here. Divide you by cosine squared theta. I'm going to divide you by cosine squared theta. And I'm going to divide you by cosine squared theta. Cosine squared theta divided by cosine squared theta, that becomes 1. Plus sine squared theta divided by cosine squared theta. That's not an exponent. Cosine squared theta. That equals 1 over cosine squared theta. Now remember, and I need some space to write this out. Remember that tangent of theta is equal to sine of theta divided by cosine of theta. So I'm going to plug that in here. So our second Pythagorean identity right now is 1 plus tangent squared theta, and that equals 1 divided by cosine squared theta. Okay, so to find the first one, we divided our original Pythagorean identity. We divided everybody by cosine squared theta. To find my second one, I'm going to divide everybody. Let me learn how to talk. To find the third, I just found the second. To find the third, I'm going to divide everyone in the original Pythagorean identity by sine squared theta. I write this down so I don't get lost, and I didn't read it. Come on. So we're going to divide everyone in here by sine squared theta to create our third Pythagorean identity. Okay. This is going to become 1, and I'm going to be left with, for now, cosine squared theta divided by sine squared theta plus 1, okay, I can draw the number 1, equals to 1 divided by sine squared theta. So I'm going to come back one more time, and I'm going to get the fourth goal. And we're going to introduce secant theta, cosecant theta, cotangent theta, and we're going to plug them into this. So I'll be back. Let me erase everything and be back for the last time. So I'll be back. I'm back for the last time, I promise. We're moving on to our fourth goal, defining secant of theta, cosecant of theta, and cotangent of theta, and we're going to insert these into our Pythagorean identities. Now, this order doesn't match this order. It doesn't bother me. Hopefully it doesn't bother you like this doesn't bother me. But anyways, let's move on. Secant of theta, which is pronounced secant of theta, is equal to 1 divided by cosine of theta. Cosecant of theta is equal to 1 over sine of theta, and cotangent of theta is equal to cosine of theta over sine of theta, or it's equal to tangent of theta. So I'm going to use colors in the equation to show you, well actually, again, I need to read what I wrote. Here are Pythagorean identities. Cosine squared of theta plus sine squared of theta equals 1. If I divide everybody in this original Pythagorean identity by cosine squared theta, I get 1 plus tangent squared theta equals 1 over cosine squared theta. And if I divide everybody in our original Pythagorean identity by sine squared theta, I get cosine squared theta over sine squared theta plus 1 equals 1 over sine squared theta. I'm going to now substitute secant theta, cosecant theta, cotangent theta into these, and we get the following Pythagorean identity. So this guy is this guy, and it's going to get replaced with this. All right. So that's going to be our first Pythagorean identity that's rewritten. So this guy becomes 1 plus tangent squared theta equal to secant squared theta. The second, or the third equation, I have actually 2. Cosine squared theta over sine squared theta, that's here. And so I can replace that with cotangent of theta. And the second substitution I'm going to do is 1 over sine squared theta. That's here. That's cosecant of theta. All right, so let me substitute that in, and I will be done with this marathon of a lesson. Here we go. So cosine squared theta over sine squared theta becomes cotangent squared theta. And I'm going to add that to 1, and that is equal to 1 over sine squared theta becomes cosecant squared theta. So hopefully you understand where all of these equations come from. Hopefully we learned a little bit more about the Pythagorean theorem. Hopefully we understand how we related the Pythagorean theorem to the trig ratios. And then we divided this original equation by cosine squared theta, sine squared theta, got our second and third Pythagorean identities, defined secant theta, cosecant theta, cotangent theta, and substituting them in. Now we don't have any fractions, so that's nice. So I'm going to end it here. Again, I hope everyone is doing all right out there. Have a good day, everybody. Bye-bye.